control. Field weakening control. All right. So field weakening control does not apply to all DC motors. Okay. This is particularly for DC motors that have an electromagnetic field, or a wound field, as we call it. Okay. Now, can you guys kind of think or predict what this is going to do? Field weakening control. What are we trying to do here? Have any of you heard of field weakening control? Maybe other than me talking about it? Yeah, actually, that's a good point, Garrett. So let's see what we're trying to do. So we're going to control, more like not control, but extend beyond the range of operation. Because when you think of a control, it's kind of, this control is misleading. When we talk about regular control, it's more like controlling torque through current, or controlling speed by measuring speed and then through a feedback loop, right? With field weakening control, we are actually extending the range of operation by influencing the field, and this we can see mathematically too. And I'm sure some of you are, yeah, so that's what we are heading to. Okay, so we'll talk about it, and I want to first of all draw the DC motor, just the electrical circuit first. So we have a resistance, we have an inductance, and then we have our back EMF, right? So we have these three elements. Now, what generates this back EMF? What causes that back EMF to develop? What are the factors? What are the factors that influence the back EMF? Okay, all right. So I'll say, yep, Garrett, you're correct. So we have the speed. What else? So we use the symbol EA. So of course, back EMF will be influenced by the speed. If you change the speed, your back EMF will change. What else? What are the other parameters that are going to influence your no? Okay, yeah, so the torque constant, of course, right? Torque constant is going to be, right, so torque constant, which we call which is same as in terms of the value, the KE, the back EMF constant, right? We know that under SI units, KE and KT are the same, or almost close. Not the same, they are very close, right? So we can, by measuring back EMF constant, we know our current and torque. Morgan, do you mean factors that influence back EMF, current and torque? Now, current and torque are indirectly influencing, because current results in electromagnetic torque, right? Current results in electromagnetic torque, and then torque passes through the mechanical dynamics before we see a speed change, right? We know that electrical time constant is relatively faster than the mechanical time constant. Therefore, it propagates through the mechanical system and then influences speed, because we have a low torque and electromagnetic torque that interact. And then that's what results in the speed, and that speed directly influences your back EMF. EA, right? So we typically write EA is equal to KE omega R, KE omega R, right? This is our back EMF constant. Now, if we go further into this back EMF constant, we can say that there is what is inside this. What are the factors that are contributing to this KE? If you think of the fundamentals of DC machines, what parameters can you think of? Yeah, exactly. So you have your windings. What are windings doing when they are rotating? What is the what effect? What law do we have to think of? So it's rotating in an electromagnetic field, right? Okay, so those windings are cutting through flux lines, right? The flux lines. Ampere's law, or Ampere's law is for something else, isn't it? There's another person just like Ampere that we need to remember. Yeah, exactly. Faraday's law of induction, right? So when there's flux line, when there's a loop of a conductor cutting through those flux lines, you will see induced EMF, right? So that's exactly what we're going to do now. What that means is you'll have some function of flux or flux density contributing to this KE. Okay, so what that means is if we have a DC motor, your KE is going to be constant, more or less. Let's assume it's in the linear region, not saturated, because with saturation you see other effects happening. However, in the linear region, magnetically linear region, your KE value is going to be relatively constant, right? Now, for a DC motor, if we want to change the flux density, right, which is the strength of the magnets, what can we do? Can we just, easily change the flux density of a magnet in a DC motor? Oh, not just a DC motor. I mean, any magnet, right? You have a magnet. If it's a relatively strong magnet, can we change that flux density very easily? No, yeah, not really, right? You can't change it. However, we know a mechanism or a method to generate a magnet which we can control, right? So we know from physics, and even in this class we have learned there is one method that we can use to develop a magnetic field or flux that we can electrically control the amount of flux that it's generating. What is that? Do you guys recall any of that? How can we generate, what do we call that if we generate a magnetic field? Yeah, exactly, electromagnet, right? So instead of using a permanent magnet, if we have a wound field, okay, let's say that means we have a magnetic field. We replace those permanent magnets with a field winding where we can control the amount of voltage, or we can control the current flow through that field winding. And by controlling that current, we are controlling the flux that this motor sees. Okay, so we'll call this IF. So we are controlling the amount of flux the machine is going to see. Now for a given motor, if we don't change any parameter in the motor, okay, and we are only changing the flux density or the total flux by changing current, guess what parameter in the motor gets influenced? It's going to influence our KE value, right? And so will our KT, right? Because KT is also flux based. So if we say TEM, if you go back to those, basics that we looked at with that one loop DC motor, electromagnetic torque is a function of flux. So TEM, you can say this is equal to KT times the armature current, right? IA. Now, if we change this flux density or total flux by changing this field current, both your KE and KT will change, right? And they're going to be in SI units. They will still be the same or close. I keep saying it will be the same, but it's not going to be the same. They will be very close. However, they will be lower than before or higher than before. They're different. Is that understood? Is that clear? What will happen with if you change the current, we are changing the total flux and the flux density, and in turn, we are influencing only KE and KT. Okay. All right. So that's step one in trying to learn about field weakening. Okay. So the next step is to go see how we can use this. And feel free to ask questions. Okay. I'm gonna go to a different page because we might just need some room here. So field winding mathematically interacting with. Okay, so now remember, we have a field winding, right? And we have what? We have the rotor winding, the armature winding, right? So imagine if you go back to our little simple DC motor that we made with permanent magnets, right? We said look like this. Gonna try to do my best here. So remember this motor, the one that had a loop of conductors like this. You guys remember that, right? So we said this is a north and this is a south, right? Now imagine us getting rid of this north and south, but we are replacing them with electromagnets. Okay, electromagnets. Now you can control the magnetic flux or the flux density as well as the amount of flux generated by those electromagnets, and they're not going to be fixed like the permanent magnets. Did I answer your question, Garrett? Okay, yeah, so we're basically replacing these permanent magnets with an electromagnet because now we can control that flux density. Okay, this is more common in large machines and more back in the day before we have we started to use AC machines. And with AC machines, this field weakening concept is practical, and we'll talk about that later. Will be touched on, so maybe. So Okay. Yeah. So it's coming, Garrett. Yeah, I think you're asking how does IF and VF interact with EA or speed? Yeah. So for now, just understand that we just replace them with electromagnets with IF. Now we can control the flux density of the magnets. Okay. Okay. So now let's go to our famous, what's that? Our torque speed, the steady state torque speed relationship for a DC motor, right? We said steady state torque speed relationship. We can write this TEM is equal to minus KE KT over RA times omega m plus KT over RA times VA, right? We've seen this, we've had this for breakfast, right? Hopefully you guys did before the exam, right? Now, if we go to our torque speed, so if you look at the operating region, so let's look at the torque versus speed plot. Okay, so this is where we study the characteristics of this DC motor, and this is for the DC motor. Now, again, don't propose wound field DC machines for small low power applications because it's not very effective. This is more common in high power machines. And the reason I'm covering this right now is when we go into AC machines, I'll show you how you can apply this from DC machines to AC machines, and then it becomes very useful. Okay, and then you'll see, oh, now we can, that's another advantage of having this capability for AC machines. So it will be much clearer and much useful, and it easier to understand rather than jumping directly into AC machine field weakening control. Okay, all right. Now we know that with our field winding, we can control this, and this, right? That's the only parameter that we can control by adjusting our field winding. Okay. Now, we also talked about in our torque speed characteristic curves. When we look at the torque speed profiles, we have certain limitations, right? So let's say this is our electromagnetic torque in newtons. This is our speed, motor speed in radians per second. All right. We said depending on the capability of the motor, the thermal capability, we kind of draw a boundary, right? We called it a safe operating region for the DC motor, right? Do you guys remember what that looked like? Anyone recall? Kind of looked like this, right? It kind of looked like that. Okay, and we briefly discussed about these different operating points and characteristics. Is this something familiar? You guys recall this? Yes? Okay, good. Now, here we actually outlined, so this is 0, 0. And now keep in mind, this is not going to be in the same proportions. This could be shorter, this could be taller. It comes in various different scales. I'm just showing one for your understanding. So depending on the application, make sure to look at the data sheet and see what it would look like. Okay, now here, can you guys name these operating points? Okay, we said we can talk about a couple of different operating points here. Okay, so what is this? What did we call that operating point? That's the stall, exactly. That's the stall condition, right? That is the stall condition, because your motor speed is at 0 and you are at maximum nominal current or steady state current, or the continuous current you can hold the motor at. Okay, and then what is this? What is this? What is that called? What is this operating point called? Rated. Yes, very good. Rated. We call this rated because this is the rated continuous operating point for your motor. Okay, now typically, for a good engineer, when you select this, you're choosing with certain safety margins for your motor to continuously operate, given the thermal capability of your material, your system. All that has to be taken into consideration. There's some flexibility there. When you design, you don't get exactly where you want it to. So just keep in mind, this is not going to be set in stone for a motor. You change your cooling system, this point could change. Okay, so keep that in mind. Now we have control over voltage in this equation, right? Our voltage is a variable that we can control also. This is the voltage that we apply to the motor, right, to generate current. Now, for that rated voltage, if we apply that rated voltage, if the parameters are maintained, the flux density is maintained at the rated value, what will the motor operating curve look like? If we maintain the voltage, we are not going to be at a certain torque or a speed. We are saying we have a curve for that, right? That defines the operation characteristics. What would that look like? That's going to be it's going to look like a straight line that passes through this rated point. Is that does it have a positive slope or a negative slope? Negative slope, right? So this is going to have a negative slope. Now, if you project this velocity, if we project this point down, okay, we project this down all the way down. Okay, this is our rated speed of the motor. Okay, now depending on the different parameters of the motor, this motor operating curve at selected VA is going to have a certain angle. It could be like this, it could be like that. Okay, it could be closer or further away, and that's depending on the different machine type. I will draw it so that it shows the exaggeration between the two the zero torque speeds, but it's not going to be that big of a difference for certain machines. So keep that in mind. So let's say I'm going to draw this in dash and then draw a continuous line here. Okay, now one more question. What is this operating point? Can we give a name for this? Now think, this curve is for VA rated. This is the rated voltage for this motor. That means we cannot exceed that voltage. I mean, you can, but it could cause some damage to the motor. So typically they specify a rated voltage. So at that rated voltage, we have this operating curve. What can you say about this speed right here? What can we say about that speed? Okay, okay, that's good. Yeah, that's one way to look at it. VA over KE. Good, Levi. What else? VA over KE. What else? Okay, so that's the no load speed. No load speed, but no load speed could be at any point, right? Depend if you change the voltage. This is no load speed for what voltage? Exactly. So this is the no load speed. This is omega no load at the rated voltage. Okay, that's the rated voltage. So now imagine you cannot exceed that voltage. Okay, it could be 10, it could be 12, it could be 40. You cannot exceed that voltage. All right, so, or you are limited by your power supply capability. Okay, so that means you can only operate along that region on this curve, right? Now, however, I wanna let's say I'm here, I'm operating right around here. I'm operating right around here. Actually, before we go to that operating point, right? Now this, if you look at this flat or the plateau part of the curve, right? This is, we are showing that the torque is constant. The torque is maintained constant, right? So if the torque is constant, what can we say about the current applied to the motor? Now we have to think very carefully before we you know. So torque is constant. We know TEM is KT times IA. So along this curve, is current changing? Current is not changing. Current is not changing. What is changing then? So along this curve, what variable is changing? If I, exactly, speed is changing. Speed is changing. So if speed is changing, what's voltage is exactly the applied voltage VA is changing, right? So that means we have a set of curves that as we change the voltage, it's going from here to here to here to here, but it's just at that operating point because we are maintaining that current to be constant. How does the voltage change but not the current? Now, assume if you have a current regulator, easiest way to look at it, right? Easiest way to look at it is if you have a current regulator, if we say maintain current at 10 amperes, that 10 amperes will be maintained and your speed will now adjust based on how it interacts with the load. Is that correct? Is the easiest way to explain that is because if you think of an open loop system, right, if you assume an open loop system, then if you change voltage, then your current is going to change, and then it's going to affect your speed. Which equation? Oh, you mean the voltage equation, right? True, that's right, So let me use my sheet. So if we write the voltage equation here, right, we can say VA is equal to RA IA plus LA DIA over DT plus KE omega R, right? So if you change your voltage, right, if you change your voltage, then yeah, of course, in the open loop setting, your current could change, may not, but what we are considering is we are maintaining current constant, right? So when we maintain current constant, then our only variable is our speed is going to change. Okay, so what I'm trying to get across here is along this line, if we think of power is voltage times current, and current is constant, voltage is being linearly increased because speed is increasing. So you'll see that your power is going to linearly increase like this. Okay, your power is going to linearly increase like this. And then when you hit this rated condition, when you reach that rated condition, now you are at a maximum. You can't provide, or you cannot pass more power than this rated condition, because it will dissipate more energy, more heat, right? Or it's not rated to handle or deliver that much of power. Okay, now from here onwards, now we only have a constant power region, so we call this this region, right? Now keep in mind, this is power, this is torque, two different things. Okay, so here we call this constant power region, constant power. And what is this region? What is constant in this region? We are only thinking of this line. Okay, we are not talking about the below those lines. If you're thinking of just moving along this line, this is constant current, right? Or constant torque. You can say constant current or constant torque, right? So you can operate, and the key point is now you have a limitation in power for your system, right? So now you've reached your rated system, okay, and now you can even move along here, right? You can move along, because if you think of it, you are at a maximum torque here and a maximum speed here. Okay, maximum torque and a maximum speed. In comparison to that rated operating point, what can we say about this operating point? In comparison to that rated operating point, what can we say about torque and speed? What can we say about? Exactly, less torque, more speed. Less torque, more speed. Now, this should make sense if we go to our voltage equation, right? So I'll rewrite it here, VA, and I'm going to write just a steady state, which means the inductance term disappears. So RA IA plus KE omega R, right? So now your total voltage, you are at a maximum here, can't change voltage because we set it to the rated value, right? You have two voltage drops here, back EMF and resistive drop. Okay, so what you're trying to do here is you're sacrificing torque to achieve more speed. You guys see that? By reducing the amount of current that is going into torque production, so TEM is KT IA, right? So you are sacrificing your current, which will help us save some voltage. So when you drop the current, you have more voltage left over for us to use to get to a higher speed. Do you guys see that? That's the next step we want to properly understand. Okay, so we're sacrificing some current, we decrease current, therefore we reduce the voltage drop from the resistor, which means now we can go slightly higher speed, which builds up back EMF. But that's still traveling along this line. Fair enough? Fair enough? Okay, all right. Okay, so now since you guys have that figured out, now we are going into the next step of field weakening. So this is where the true field weakening is going to apply. Okay, now that means, this means we cannot cross this line. At this situation, if we don't do anything else for these parameters, for what we have, we cannot go beyond this because we are capped at our rated voltage. We are at the maximum torque. This line won't let us go beyond that because we don't have energy to go, right? So what can we do now? What can we do now? Based on this idea of field weakening, if we have another knob to control, right, that'll be wonderful, right? We can now control another parameter. Exactly. Right? So we can either increase KE or decrease KE. If we have a knob to control that, we can use that to our benefit. Okay, so if we decrease KE, okay, if we decrease KE, let's think of that. What will happen? If we decrease KE, what's going to happen? For the same voltage, we will see less back EMF. For the same speed, we will see less back EMF, right? If we decrease KE, for the same speed, our back EMF will be lower. Okay, and in the meantime, what can we say about torque? Now we changed KE, so KT is going to follow, right? So for the same amount of current, what will happen to the torque? The torque will decrease. Okay, torque will decrease. However, now we have more voltage left over to go to a higher speed. You guys see that? So I think of it like operating in this region, right? So if you want to move slightly further from here, we will change KE to a smaller value. However, because we changed KE, let's say we lowered KE, because when we lower KE, we have more voltage, or our back EMF will decrease. However, our torque will decrease too. Our torque, electromagnetic torque capability will also decrease for that same rated current, right? And then your back EMF will drop, your rated current, your torque will drop. However, we can now go past this rated voltage operating line. Okay, so that means now we can reach operating points here, here. Okay, we can reach those operating points. Do you guys see that from the equation? If we change Ke for the same speed, we have less back EMF. That means with that we're going to lose the torque, so our total electromagnetic torque will drop. However, we can reach a higher speed for that same amount of current. Is that clear? Is that cool? Yeah. Okay. So we need to look at one more thing here. Now, so when we changed Ke, if we what will happen to our characteristic curve, the motor operating curve? Will it stay the same? Right. So if we did, so field weakening is basically changing Ke, right? You're reducing the amount of field current. And when you do that, you changed Ke. Let's say we reduced Ke, right? What can we say will happen to our operating curve? So it's going to move right like that. Pivot counterclockwise. So like that. Right. So exactly that's what's going to happen. Okay. It's going to be linear. See, linearity is not affected. Okay. So when you change your Ke, your Kt will change. Therefore, your slope is definitely impacted, right? And then what does this tell us? This tells us our no load speed. That's also impacted. So essentially, you're going to have a curve with a different slope and a different x-intercept. Okay, so with this new Ke, I'm going to try to find a color here that's not going to confuse you guys. We have red, orange, blue. Well, I'll use this black one. So now, so not to confuse, and this is going to be an exaggeration. So your new curve, and this is, I'm going to only draw it something like that. Okay, so this is the field weakened operating curve. Okay, so now you can actually do more than just this. You can, by changing Ke as much as you want, you can change how it operates along this curve, along at the rated value. So this is constant power, right? You can operate along that line, or you can operate within this region as well. Okay, is that clear? Any questions? So you influenced your the what's that? I forgot the slope. You change your slope as well as your x intercept. Both are affected. Good. So this is called field weakening control. If you want to reach higher speeds and not deliver the same amount of torque, so you're now kind of at the peak power capability of your power supplies, you're optimally using them to go to a higher speed without changing the machine design. You're influencing KE. That's not, I don't think that's considered changing machine design. Kind of having a variable to control to get to those higher speeds. Okay, good. This used to be applicable more for machines that are operated, that are used in power generation, very large machines, wound field machines. There are different type of machines when it comes to DC, parallel field, series field, and this is applicable primarily to those. Now, more recently, the application has become in the three-phase machine area, where you have three-phase machines, and now we can actually show mathematically that you can control both field and magnetizing those two field, the flux, the stator and the rotor flux. Actually, the rotor flux can be influenced on a PMSM using the same concept, and we'll talk about this in detail. Okay, good. Do you guys have any question on this torque speed on field weakening? Does this give you a good idea of what it is? And if, let's say, you have to explain it to someone, can you do that? Yes. Okay, good. All right. So I'm gonna stop the recording. Let me see. There we go.